again, can you give me the two functions? That's all the stuff we talked about Friday and Thursday. But can you also tell me when the object is stopped? I don't know if you can or can't. I'm just interested. So you have access to, I know you can do this on your phone probably too, but remember, you don't have that on the AP exam, but you can use a graphing calculator. My expectation is finding the position and the acceleration should have been very straightforward. At this point, if you're still having trouble with that, I can hook you up with a ton of practice, but there's also a ton of practice at the end of your chapter in your textbook. The odds, their answers are in the back of the book. But let's do the easier one. Let's find the derivative. That would be finding the acceleration. So I'm going to take the derivative of this function. Bring the 3 down, subtract 1. There's just a polynomial function. Going to the next term, 2 times 6 is 12. T to the 2 minus 1 is t. And then t to the 1 power, so 11 times 1 is 11. So that's it. I take the derivative of the function, that produces the acceleration. We're only dealing with polynomial functions, so that's my expectation. Saw that on many papers. Not 100%, but on many. The other direction, I need to add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. And if there's no variable for t there, well then it's t to the 0 power. Add 1 to the exponent, divide by the new exponent. Now, I didn't tell you where the object started, so I need to make sure we add a constant in here to remind ourselves that we don't know where the initial position of the object is, the position at time 0. But these can all be reduced down to their simpler forms. Saw that on many papers too. That's good. Glad to see it. Finding the time when the velocity is 0, that might have been harder for some of you. That means finding the root to this function. Who used your calculator to do it? How many just used the graphing function of the calculator? Okay. Anybody do synthetic division? Not bad. I mean, they were integers, so that kind of helped. Anybody do grouping? Okay, so our two methods are synthetic division and using your calculator. It's going to be faster to use your calculator. Synthetic division also will work, but it's a lot harder if they're not, if it's not integer solutions, correct? That would make it more challenging, but the answers were t equals 1, 2, and 3 seconds. Now, it is incredibly unlikely you'll be required to do that. For the most part, if you're given something like that, they'll probably give you one of the roots to turn it into a quadratic. That way you can remove one root, move on. Does that make sense? So they might say that they know that it has a velocity of 0 at time equals 1 second. Find the other 2 times where it has a velocity of 0. That makes it a little bit easier because you've reduced one of the roots. You can divide out that root and you get a quadratic, and that makes it more straightforward. But they are very seldom going to ask that question. I just wanted to see who was capable of doing it. I've finally gotten around to looking at your math pretests, and I'm getting some ideas here. However, I'm not quite done with seeing what you're capable of doing yet. I'd like to throw you a curveball and see if you guys can work with it, okay? I don't want anything crazy. I'm just looking for position function and acceleration function.
Is that 6 over t squared?
6 over t squared, yes. Maybe you have forgotten this. So let me remind you, this could be written as 6t to the negative 2 power. Does that change maybe what your answer is? It's going to change some of your answers, yes. many of your answers. Many of you did not know that. It's still a polynomial, though. So let's do the derivative first. I bring the 2 down. 2 times 6 is 12. And subtract 1 from the exponent. T to the 2 minus 1, which is just t to the 1. Negative 2 times negative 6. So negative 6 times negative 2. And then subtract 1 from the exponent. So t to the negative 3. And negative 2 times negative 6, positive 12. So it can be treated just like a polynomial, because it is. The other direction, add 1 to the exponent, divide by the new exponent, so 6 divided by 3 is 2. We just saw that one, so. And yeah, I'm not writing out all the steps anymore. I don't think I need to. Add 1 to the exponent, so negative 2 plus 1, and then divide by the new exponent, so minus 6 divided by negative 1. Any question there? I mean, we can reduce it down. This will be positive 6. And negative 2 plus 1 is going to be negative 1. Yep. Yep.
If they were to ask for this on like an AP, would they prefer with a negative exponent?
They don't care.
Okay.
They don't care. Alrighty. Wasn't trying to throw too big a curve, but I think this was not unreasonable to ask. We're going to do something different today. And I want you to understand that this is going to stratify the room a bit. There might be 4 groups here. I've been thinking in my head there's only 3, but there might be 4. I have a group of you that are in pre-calc, so a lot of what we're doing here, all of this, brand new. And you don't have the skill set yet from what pre-calc will give you. So that is a lot of function work that you haven't done yet. There's the folks who are in calculus right now, so you don't know this stuff yet either. You're still working probably limits and stuff. BC might be past that by now, but AB not so much. And you'll be getting into this very soon if you're in AB, and BC is in this now. But what we're going to do today, BC hasn't done yet. I'm sorry, AB hasn't done yet. Then there's people who have had AB already, and they're in BC. Everything we do in here you'll know how to do, except for, one part of it, perhaps. Now, I think there's a 4th group, and that 4th group is a group that you couldn't do the algebra, and so you're in trouble now. And this stuff, you're not able to do it. And I'm going to be honest with you, that this is a skill I need you to have. So we're going to move on to something else today. It's the same stuff. It's just I'm adding a little bit to it. And this is to help address problem number 4 in the homework. For those of you who have the skill, I want you to try it. After today, I want all of you to attempt it. But I want to be clear that I don't know that all of you will be successful, but I want you to do the parts of this that I think you are capable of doing. By the end, I will show us the entire thing that we've done, and I will circle the stuff that is this class specific and the sections that you would need to know calculus to do. Does that make sense? All right. So also, as we go about doing this, I'm going to tell you if I think this is something that everybody can do at this moment, or should be able to do at this moment, and which things I would not expect you to be able to do at this moment. Today we're going to talk about differential equations. And don't think too deeply into it. A differential equation is just an equation with a differential in it. It's not much there. The first thing I want to propose to you is that you will have to create differential equations as part of a matter of course in this class. But you already have some differentials at your disposal, or at least we've talked about some. A way of writing velocity is in its differential form. Its differential form is dx dt. It indicates that it is the rate of change of the position, and we have defined that as velocity. But v is dx dt, in the same way that we have defined acceleration as dv dt. dv dt is the differential form of acceleration. Acceleration is the rate of change of velocity. And we also know that acceleration can be written as a second derivative, but we're not going to get into second derivatives or their equations today. We're going to deal with just first order differential equations. Now, to give us a starting place, I need something that might have some form of differential in it. So I'm going to talk about something that will be coming up in about 2 weeks' time. We'll be getting into dynamics soon, which is Newton's laws. And in Newton's laws, we learn about forces and how they cause objects to accelerate. You don't need to know any of that for what I'm about to talk about, but I am going to use a specific example of a car that at time 0 switches off its engine while moving. So switches off its engine and just coasts. The vehicle is going to be brought to rest by a combination of friction and air resistance. Well, what you don't know is that air resistance is something called the drag force. And the size of the drag force depends on how fast you're moving through the air. The faster you move through the air, the more drag you experience. It's not critical to understanding what we're going to do, but it's something that will be part of our coursework. Now, writing that as an equation ends up looking like this. This says the same thing I just did, that the acceleration experienced by an object that is having wind resistance is proportional to, oh wait, not t, sorry, it's supposed to be v. I'll say that all over again. The acceleration experienced by an object is proportional to how fast it's going. It's a negative because the acceleration will be in the opposite direction of your velocity. So if you're moving forwards through the air resistance is trying to stop you. Does that make sense? That's why there's a negative sign there. The m here stands for the mass of the object. So that's a constant. Bigger objects are harder to stop, so this acceleration has less impact on the bigger object. C, this proportionality constant, is called the drag coefficient. If you have a nice, car that has lots of smooth lines, it probably has a small drag coefficient. If you drive a old beat-up Jeep like I do, it probably has a large coefficient. I get more drag for my velocity than a sports car gets. Does that make sense? Now, you don't have to understand all of the things I just said. What you do have to understand is that C and M are constants. They're not changing once the problem starts. The mass of the car and its shape stay the same. A is the acceleration that the cars experience, but it changes over time because the car's slowing down. So the drag is getting smaller. The first thing you might be asked after creating this function is to create a differential equation that could be solved to describe the velocity of the car. Does everybody understand what I just said? That's a statement that we'll be looking for. Create a differential equation that could be used to describe the velocity of the car. Step 1. We're going to create the differential equation. This is not a diffie-q right now. This is just an equation, but it has two variables in it that are related. Acceleration and velocity are related, and acceleration and velocity can both be written as a differential. To create a differential equation, all we have to do is get a differential into our equation. That's all a differential equation is. It's an equation that has a differential in it. So we need to substitute in a differential. Now, I'm not going to write all these steps out, but that's what you're going to try and do. So in step 1, create the differential equation. Your thing to do is to substitute a differential in for one of the variables. Now, we only have 2, so it's going to be one of these. Your goal, though, is to try to reduce the number of variables. We currently have 2 variables, acceleration and velocity. We want to substitute in a differential that reduces the number of variables. For example, one way to do this would be for me to substitute in dx dt for velocity. That is a differential. I have created a differential equation. But you'll notice I did not reduce the number of variables. I just exchanged velocity for position. I still have 2 variables now. This substitution created a differential equation, but not one that I can solve. So this was a poor choice. I want to reduce the number of variables, not increase the number of variables. So let's go with option B. I'm going to substitute in dv dt for acceleration. This substitution puts everything in terms of velocity. I have reduced the number of variables because now with my substitution, I have something that has to do with velocity on the left and velocity on the right. Do you see what I'm saying? You only have 2 choices, and we will only have 3 differentials all year. So these are 2 of them. So in creating a differential equation, it's either subbing in for acceleration or subbing in for velocity. Your goal is to try and reduce the number of variables, try and match what's there. So that's it. That's step 1. You're done. You have created a differential equation. Unfortunately, oftentimes, the very next question is, now use your differential equation to solve for a function of velocity. So that's going to be step 2. We want to solve our diffeq to create v as a function of t. We want to create a function for velocity. Now this has many more steps. This is where the real work begins. But it's kind of nice to know actually you usually get a point for creating the differential equation. 1 whole point for that substitution. So let's do step 2. We want to solve our diffeq to create a function for velocity as a function of time. I'm going to give you a series of things to do. So if this is step 2, then part A of step 2, I want you to isolate the differential. Isolate the differential. All this means is to get the differential by itself. So for that, I'm going to divide both sides by m. I have a tendency to group the constants together, but this is the same as writing CV over m. But some people in 3rd and 6th period didn't realize that. So this and this are algebraically the same. We all okay with that? All right. I hope so. Next step. This whole process is called splitting the differential. That's what the whole process is called, but this is the step where you actually do that. Splitting the differential means separating the fraction. Remember, this is just a fraction. So to split the differential, I multiply both sides by whatever the bottom of the fraction is. In this case, dt. Now on the left side, the dt's cancel out, leaving me just with dv on the left and a combination of things on the right. Constant times velocity. Now, the next step is to collect variables. You see, to continue this process, we need to get everything that has a v in it on the side with dv, and everything that has a t in it on the side with dt. So collecting variables means to get the function variables on the same side as your partial fraction. So I need to get the v's on the left side and all the t's on the right side. Everybody good with that? Well, that looks to me like just dividing both sides of my function by v. If I divide both sides by v, I will get 1 over v dv on the left side and just c over m times dt on the right. I divided both sides by v. There are no t's, so I don't have to worry about getting t on the other side or anything like that. In fact, like in the past, because I'm going to be doing some integration here in a minute, there's an implied t to the 0 power. I'm just going to put it in there. I'm going to put it on the side with dt, because there were no t's. In a calculus class, you probably wouldn't do this. I'm doing this in here just to make sure we represent and reflect on what we've been doing in the past. All right, the next part. Here's where calculus has to be brought to bear. And although what I'm about to do next is not something that is necessarily taught in calculus, it's something that you would have to learn probably from me, this is where we begin the calculus. We want to get rid of the dv and the dt. And the way to do that is by taking the integral of both sides. We've been playing at this for a couple of days, but we're going to do the real thing. And so all that really means right now is to draw a symbol on both sides of the equation. This is the integral symbol. Now, if you've never seen the integral symbol before, it's just a fancy S. It's on purpose because it's supposed to represent a summation. And my experience is that you guys know what summations are because at this point, everybody has seen the summation symbol. Help me out here. Something goes on the bottom and top of the summation. Do you guys remember what goes in the bottom and top? Do you know how to set up a summation? Yes, sir. Go ahead.
At the bottom, you're at starting point, like n equals something, and at the top, you write ending point.
Right. So the bottom is our starting point, and the top is our ending point, usually referring to integer values. For example, what if I want to do the summation of x to the n power, where n starts at 1 and ends at 4? This is how I would write that symbolically using the summation symbol. And this should mean something to all of you. For example, you guys know what this would mean to do, correct? It would start with x to the 1 plus x to the 2 plus x to the 3 plus x to the 4. You have a process in mind for how to deal with the summation. At least you're supposed to. If you don't, I'm just trying to remind you of past work. In calculus, the summation symbol arguably means the same thing, except you spend a year of calculus or more trying to figure out different ways to do the summation without actually doing a sum. There's a process. It feels a little bit like, something that's been made up. But you guys are getting to the fundamental theorem of calculus, will know all about it. We still have to place something at the bottom and top, a starting point and an ending point. Now, this is a little different for here, so I want to rewrite this because our next part is setting our limits. One of the things I would encourage you to do is to get the constants out of the way so you can focus just on the integral. So I've pulled the constant out front. Because we're taking the integral of both sides, we also have to set common limits both at the top and the bottom. Now this part may not make a lot of sense to you. It may not make a lot of sense to those of you who finished Calc AB, but this is what we do in this class. The bottom limits have to be joined together, and we already actually have bottom limits. At time 0, the velocity was v0. It's a common limit that we set for both. We said at the start of this problem, time equals 0, the car was moving at a velocity of v0. So I have a common bottom limit. You have to always find what your common limits are because we're integrating both sides and they represent the same moment in time or same activity that you're observing. The difference is we're trying to create a function. Because of that, the top limit represents some time in the future. I'm just going to put a t there. If you don't like the fact that there's t's everywhere, put a capital T there. I don't care. But you need something that indicates between you and I that it's some time in the future. And on this side, we're looking for some velocity at that future time. So I'm going to put the functional notation in for velocity. V is a function of t. I'm finding a future velocity. Setting our limits. Again, this part, stuff that you still have to get from my class, you get a little of this in calculus. But the next part, this is pure calculus. Do your calculus. An integral has two parts. You've already done one part, but it has two parts. The first part is finding the antiderivative of your function. The second part is applying the limits. We've done the first part. For example, it should not be a surprise what to do here. This says take the antiderivative of t to the 0 power with respect to t. This is just the symbols that are used. This is a polynomial, and we've done this polynomial before. So I have t to the 0 power. I'm going to increase 0 by 1 and divide by the new exponent. That's it. I've done the antiderivative. I've not applied my limits, so I'm going to put a bracket here and put in the limits on either side of the bracket to remind me to substitute in my limits. So again, taking an integral has two parts, antiderivative first, and then putting in your limits. This is all the calculus. Now here's the part that is going to be a problem. We're going to have a problem using the polynomial rule for 1 over v. If you don't know why, then think for just a moment what we've been doing for polynomials. V to the -1 power. If I try to use the polynomial rule, I'll get v to the -1 plus 1 divided by -1 plus 1. Do you see why that's a problem? Can't divide by 0. But anybody who's had a course in calculus understands that every function, except for a very narrow few, every function has an antiderivative. Might be a lot of work to get there, but every function does. There is an antiderivative to the inverse function. And I know a few of you know what it is, because one of you is chomping at the bit to tell me. Go ahead.
Natural log of v.
Yep. The natural log of v. I don't expect you to know that yet. You will have to know that by the end of the year. In fact, you'll have to know that in about the next 2 months. So there's the polynomial rules, and then there's rules for inverse functions, and there's rules for exponents, and there's rules for trig functions. Every function has an antiderivative except for a couple. We will never do anything particularly hard. All of ours are going to be pretty straightforward. You guys will learn all sorts of processes to deal with antiderivatives and more complicated functions as you take calculus. We only do simple things. Now, you might not understand this yet. Fine. I don't care. I said not everybody will be able to access what we just did. However, from this point forward, everybody can. Everybody. Because everything we do now is just pure algebra. So now that we've done all the voodoo, I expect everybody to pay attention and everybody can do this. First, put in your limits. That's a process. And as a process goes, it's just algebra. Putting in your limits means you put in the top number first, and then subtract and put in your bottom number. So we're putting it in for t. So I put t in for t first, then subtract, putting in 0 for t. That's putting in my limits. I'm going to do the same thing on the left side. I'm going to put in v as a function of t. So natural log of v as a function of t. My history, my teachers beat into me that you can only take the natural log of a positive number, so I've learned to put the absolute value bars on any natural log that involves this. But you may not have learned that. That's okay. You don't have to have the absolute value bars there. But I put in my top value, subtract, and put in my bottom value. All right, so we've done the calculus. It spits this out. Now, this should look familiar because it was on your practice test, your math test. I asked you guys to solve this for v, and boy, was I surprised. You're supposed to have this skill set, but it involves knowing some things. And I found that there were some of you who didn't know these things. So let's talk about this, because this is just algebra. Do you know your logarithm rules? Raise your hand if you think you know your logarithm rules. It's okay to say I don't. All right, that's not very many. So let's talk about some logarithm rules. If you subtract logarithms, you can combine them together. Remember, we're trying to get this by itself. That's what we're solving for. V is a function of t. I got to get it out by itself. Well, one way to do that is to try and get rid of the logarithm. And you guys probably know there's ways to get rid of logarithms. Like logarithm of x equals c. Well, I can raise both sides to this, right? I can get rid of the logarithm on the left. I just got to find a way to combine the logarithm together. Well, when you subtract logarithms, you divide. If you're adding logarithms, you multiply. But when you subtract logarithms, you divide. You were taught this at one time. I'm just reminding you. Again, I want to get v as a function of t by itself. So now that I have the logarithm, I can get rid of the logarithm by writing this as an exponential. I can raise both sides to the base of e. You can raise both sides of an equation to any base you want, but base e is what I want here because it cancels out the natural log on the left. So I get that on that side and that on that side. Almost done. I'm still trying to get v as a function of t by itself. So I'm thinking multiply both sides by v naught. That's it. That's the answer. It's an exponential decaying function. Do you see that? If I turn off the engine at t equals 0, so t equals 0, I put that in. It gives me v naught times e to the 0 power. So at t equals 0, my velocity is v naught. Is that a surprise? That's what we set it to be, right? It was our boundary condition. Our answer has to be that. So from that point forward, our velocity slowly gets smaller over time. Well, I expect that. But it decays, like never approaches 0 or gets, That's because the acceleration is getting smaller as the velocity gets smaller. A couple things about this that I want to kind of throw together, and let's take a look at what we just did. That looks like a lot. It was in steps, if you'll recall. There was creating a differential equation, right? There was solving the differential equation to get a function. Okay? There was calculus. Right? Because part of solving the differential equation was just splitting the derivative and creating, splitting the derivative and creating an integration. That has nothing to do with calculus directly. That's what we are learning how to do, splitting a derivative. And then there was algebra for after we were done with our calculus. Generally on the AP exam, this is worth 1 point, and this is worth 1 point. In fact, in some cases, they will tell you the answer and say, show that when you split the derivative, you get this as your answer. Every once in a while, they give 1 point for correct calculus. Every once in a while. But remember, in an FRQ, there's 15 points, and you have 15 minutes to do it. We only will see 3 different differential equations in here. You have just seen one of them. How likely is it if we have this one again, will you remember it? Maybe not the first time, but by the 5th or 6th time, when you see it looks the same almost every time, I'm going to expect that you can repeat this process. Again, we only have 2 possible differentials, dx dt and dv dt right now. Subbing in and doing this, I'm not expecting too much. There are parts of this that are tough. This might be voodoo if you have no idea where it comes from, but raise your hand if you've had a year of calculus already. How many of you could use the fundamental theorem of calculus to show that this is true? I don't know. I'd love to see it. It's been like 40 years since I had to do it. I just know that that's what you do.